Alright, so welcome to my first video on doing wave calculations. To the top of the screen, you should be seeing 6 formulas. Right now, throughout the video, I'll be referring to these videos as we do each question. Of course, some of you may not be familiar with the formulas, but don't worry. As I use each formula, I will explain them one by one. Alright, so let's have a look at our first question here. Here we have a sound wave that has a frequency of 5450 Hertz, 5450 Hertz, and a wavelength of 0.04 meters. And this question is asking, what is the velocity of this particular wave? Alright, so let's try to figure out which formula to use. Now, we've been given the frequency. So we have the frequency here. So we're just going to put F for frequency here. Remember, frequency is measured in Hertz. And we've been also given the wavelength, which is given to us in meters. So, and we've been asked to find the velocity. All right. So this looks like a clear case of using the first formula, which is velocity is equal to frequency multiplied by wavelength. Now, in case you don't know this symbol, this is the symbol for wavelength. Whenever we are using this formula, it is preferred that the velocity is in meters per second. Frequency should be measured in Hertz, and your wavelength should be measured in meters, not centimeters. All right, so let's see if if there are any tricks in this particular question. Well, the frequency has been given in Hertz, so that's good. The velocity is what we are trying to find, and our wavelength is given in meters. So it seems to me there are no tricks in this question. So how do we find the velocity? Well, it's very simple. We just block the V. If we block the V, we've been left with frequency multiplied by wavelength. So to find the velocity, all we have to do is take the frequency and multiply it by the wavelength. Now, I'm going to try my best to keep my hands out of the way. So whenever I write something, you can be assured that I will move my hand out of the way. So to find the velocity, we just take the frequency, which is 5450 Hertz, and the wavelength is, 0.04. So let's multiply that and let's see what we get. 5450 multiplied by 0.04, right? Now, I'm hoping that you can see the calculator properly, right? If not, I can always move it up once in a while so you can see it clearer. All right, so let's see. I'm double checking my work in here. 5450 multiplied by 0.04, and that gives me 218. And my answer would be in meters per second. All right, so that's our velocity. Now, this question had no tricks in it. All the units were as the formula required. All right, so in a question like this is possible in the exam, but don't expect too much marks for it. All right, let's try a second question here. Right. A sound wave travels with a velocity of 300 meters per second. Great. So our velocity is given in the correct units, meters per second. That is what we want. And a frequency, sorry for the bad writing here, is 12, not Hertz, but 12 kilohertz. What is the wavelength? Now, it seems to me we will be using formula 1 again. So velocity is frequency multiplied by wavelength. We are trying to find the wavelength. So to find wavelength, we block the wavelength symbol and we end up with velocity divided by frequency. So to calculate wavelength, all we have to do is take the velocity and divide it by frequency. Now, there's a slight trick in this question. The velocity is okay. It's 330 meters per second. But the frequency needs to be in Hertz, not kilohertz. Now, in case you don't know, the big K stands for kilo there. So let's write it here, K-I-L-O. Kilo means you have to multiply it by 1,000. So this is really 12 multiplied by 1,000, which is obviously 12,000. So for this formula to work, we need to take the velocity and divide it by the frequency in hertz, not kilohertz. So we have to divide it by 12,000. So all we have to do is take our calculator and type in 330 divided by 12, 1, 2, 3, and we will get 0.0275. All right. Now remember, we found our wavelength, and if we use this formula properly, the wavelength always comes out in meters. All right. So that is our wavelength in meters. All right. So let's try a second set of questions for questions 3 and. All right, so here are 2 more questions. Now I've decided to remove the calculator from the screen because I don't think that you all are seeing this screen clearly. But anyway, you just have your calculator in hand and work the question as I work it. All right, so here we have another question. A wave at sea travels with a velocity of 45 meters per second. If it has, sorry for this error here, has a wavelength of 2,500 centimeters, they are asking what the frequency of this wave is. All right, so let's see if we can use the first formula again. Most likely it's still the first formula. Remember, because they gave us the velocity in meters per second, so that's the correct units. But look at this, they gave us the wavelength in centimeters. So it's a slight trick in this question. So let's write back the first formula. Velocity is equal to frequency multiplied by wavelength. This is formula 1 at the top of the screen. What are they asking us to find? They are asking us to find frequency. So to find frequency, we take velocity and divide it by wavelength. So let's try that. Frequency is velocity divided by wavelength. So how much is the velocity? The velocity is 45 meters per second, and I stress again, that is the correct units. But they gave us the wavelength in centimeters. For this formula to work, we need to have the wavelength in meters. So all we need to do is take the 2,500 and divide it by 100, because you're 100 centimeters in a meter. So if we do that, we will get 2.5. No, sir. We won't get that. We will get, sorry about this mistake here. We had 45 on top. And if we take this and divide it by 100, we will get 25 meters. So let's divide it. 45 divided by 25. And that will give us 1.8. Now remember, they asked us for the frequency. And frequency is measured in something called Hertz. H-E-R-T-Z. But this here is the symbol for it. All right, let's try another question here, right? So I noticed that these questions were not printed out properly. It's just it's a new printer I got, and I guess, well, the ink is a little dry, so it's coming out like this. All right, a wave has a frequency of 2,800, but notice this symbol here, megahertz. Capital M stands for mega, and mega means you have to multiply by 1,000,000, right? That's a 1 with 6 zeros. And a wavelength of 25 centimeters. What is its velocity? There are 2 tricks in this question. One is the megahertz, because frequency needs to be measured in normal hertz. So I will need to take this value and multiply it by 1,000,000 first to get the frequency. And notice they gave you the wavelength in centimeters. I need this to be in meters. So I will need to divide this by 100 first. So this looks like formula 1 again. Velocity is frequency multiplied by wavelength. So what are they asking us to find this time? The velocity. So the calculated velocity is frequency multiplied by wavelength. Velocity is frequency multiplied by wavelength. So the frequency is 2800, but I have to multiply this by 1,000,000. Right? So I put in some commas here so you can see the zeros. This is to convert it to normal hertz. And the wavelength is not 25, but 25 divided by 100, which is 0.25. So we just need to multiply this out and we are finished. 2800 multiplied by 1,000,000 multiplied by 0.25. Ooh, that's a lot of zeros. This is 7 with how much? 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 zeros. So it's 1, 2, 3, 4, 5, 6, 7, 8. Or you can write it as 7 multiplied by 10 to the power 8 meters per second. Because if we use this formula properly with the correct units, our velocity will come out in meters per second. All right, let's try another set of questions. Okay, let's try number 5 and number 6. Okay, so sorry about the. I'm gonna try to fix this as we go along. Oh, by the way, if you want a copy of this, of all the questions here, PDF copy, feel free to WhatsApp me. Only WhatsApp me on 1868 712 2652, and I will gladly send you a PDF copy of all these questions here. Right? All right. Cool. So let's continue. All right, let's make a note here or something. All right, so here we have a sound wave which travels at a velocity of 4.5 kilometers per hour and has a frequency of 400 kilohertz. This is Formula 1 again. Velocity is frequency multiplied by wavelength. But there are a few tricks in this question. The first one, it should be obvious. The frequency, remember what we're trying to do is find the wavelength. So let's put down the formula. If we block wavelength, we get velocity divided by frequency. Our frequency needs to be in hertz, not kilohertz. So what we will need to do is for this one here, the frequency, the 400, and remember kilo means you need to multiply by 1,000. Now the velocity is in kilometers per hour. Now how do you convert kilometers per hour to meters per second? To convert kilometers per hour, the 4.5, you have to multiply by 1,000 and then divide it by 3,600. Right? Now, if you didn't know this conversion, please go back and watch my, I have 3 videos, physics for beginners or physics basics. It's three videos. Make sure and watch all 3. It goes through simple conversions and a lot of other basics you need in order to get out the question. So let me do this calculation here to get my velocity to be in the correct units, which is meters per second. 4.5 multiplied by 1,000 divided by 3,600. And I get a value of 1.25. So how much is my wavelength? Well, simple. I just have to take this top and divide it by the underneath. 1.25 divided by 400 multiplied by 1,000. Oh, gives me a pretty nasty number here. 0.0. Let's count how much zeros. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3,125 meters per. Oh, my pen is dying on me. Meters per second. Obviously, if we want to put this in standard form, we can move it. Sorry, not meters per second. Sorry, I made a mistake. Sorry. Wavelength is measured in meters. If we want to put it in standard form, we move it 1, 2, 3, 4, 5, and 6. we will get 3.125 multiplied by 10 to the power minus 6 meters. All right, so hope you saw all the tricks in that question. Hope you understood, the tricks in the question. I showed you the tricks. All right, light waves travel at 3 multiplied by 10 to the power 8 meters per second. If the light wave has a particular wavelength of 520 nanometers, calculate its frequency. Well, this is the first formula again. Velocity is frequency multiplied by wavelength. What are we trying to find? The frequency. So to find frequency, we just block the F. That's just velocity divided by wavelength. So frequency is equal to velocity divided by wavelength. The velocity has been given in meters per second. They just put it in standard form. So 3 multiplied by 10 to the power 8. But the main thing is, this is in meters per second. Now, the wavelength is given in nanometers. Now, 520 nanometers. Now, 520 just means you have to multiply it by 10 to the power minus 9. Nano is a very small value. So, if you had watched the physics for beginners or physics basic videos, we would have gone through what the common n means, right? So I'm letting you know now, again, nano means to take the value and multiply it by 10 to the power minus 9, and then we will have the wavelength in normal meters. So let's finish this question quickly. We're just going to take the top and divide it by the underneath. 3 to the power 8 divided by 520 multiplied by 10 to the power negative 9. And, well, we will get, if we round it off, 577, if we round off the 2 decimal places properly, multiplied by 10 to the power 14, and frequency is measured in Hertz. All right, so let's try another question here. All right, so let me get a different color ink here. I'm going to use a black ink this time. All right, calculate the wavelength of a broadcast from a radio station named 108.5 Radio Kunupir FM, which emits waves of frequency 108.5 megahertz at this speed. Now, just a little fact, whenever you hear a radio station number, that's really their broadcasting frequency. So, and notice the broadcasting frequency is stated in megahertz. Mega means you have to multiply it by 1,000,000 or 10 to the power 6, right? Both of them are the same exact thing. So, let's see. What do they want us to find in this question? Calculate the wavelength. So it's formula 1 again. I made a mistake here. Velocity is frequency multiplied by wavelength. So to calculate the wavelength, we just have to take the velocity and divide it by the frequency. Wavelength is velocity divided by frequency. Now, the speed or the velocity, right? Just for simplicity's sake, speed and velocity will be the same thing in these videos. Now, I know speed and velocity are slightly different, but to make the video simple, just assume speed and velocity is the same thing. So the speed is given in meters per second. So it's 3 multiplied by 10 to the power 8. And the frequency is 108.5, but mega means you have to multiply it by 1,000,000 or 10 to the power 6. So all we need to do is divide these two, right? So divided by 108.56. And we get actually a pretty okayish number if we round it off, 276 meters. Okay? All right, so those were 7 questions so far. Let's try another one. And so far we've only used formula 1, but I did those particular examples to to show you the little tricks the examiner can play on you. I just wanted to make sure I just wanted to make sure you know how to convert things like kilometers per hour to meters per second, what mega, what nano meant, because those things are what can make or break a student in an exam. Okay? All right. Question 8. You have an EM wave. Now, EM wave is an electromagnetic wave which travels at a speed of 2.8 multiplied by 10 to the power 8 meters per second from water to diamond. So here we have a little diagram. The light wave, the EM wave is going from water into diamond. Right now, if you had watched my previous video on refraction, you know that when a wave goes from one substance like water to a different substance like diamond, the angles will change. Now, the angle here is big, and when it goes into diamond, it will get smaller. And now I know this often because water is less dense than diamond. So whenever you go from less dense to more dense, the angle actually gets smaller. You notice here is bigger and here is what? Smaller. Also, if it goes from more dense to less dense, the velocity is supposed to decrease, right? Now that if it's going from more dense to less dense. Anyway, let's go through this question and see what you're asking us. So the speed of the wave, right, from water. So let's put in all the information first. So that means the velocity in the water is 2.8 multiplied by 10 to the power 8 meters per second. So we know the velocity in water. And it goes from water to diamond where the speed is reduced. You see, the speed has been reduced when it went into diamond. So the velocity of the EM wave in diamond is a little bit smaller. It's 2.5 multiplied by 10 to the power 8 meters per second. Right? And notice the units are correct. If the angle of incidence in water, so that means this angle here is 60 degrees, right? So the angle in the water is 60 degrees. What was the angle in diamond? So we want to know the angle in diamond. So I'll just put a D here for the angle in diamond. Right, now, whenever a wave goes from one substance to the next substance, the refractive index is a very important value. You will notice that the refractive index in this question is missing. So if we look at which formula here? Formula 6, right? You will see this formula. N is equal to velocity in one medium divided by the velocity in the other medium. So the two mediums here are water and diamond. Notice I put the W first and the D after, which means that the wave is going from water to diamond, which means the W goes on top and the D goes underneath. So N stands for your refractive index. If you want to calculate the refractive index from water to diamond, it's very easy to do. All we have to do is take the velocity in water, which we have, which is 2.8 multiplied by 10 to the power 8 and divided by the velocity in diamond, which is 2.5 multiplied by 10 to the power 8. If we divide this, we will get the refractive index from water to diamond. So let's do that. So the refractive index from water to diamond is 2.8 to the power 8 divided by 2.5 to the power 8. And we will get 1.12. Refractive index has no units. I'm just double checking my answer. 2.8 divided by 2.5. Yep, my answer is correct. Now that we have the refractive index, right, we can calculate what? The angle in diamond by using formula 5. So WND, I'm quoting formula 5 here, is sine of the angle in W divided by sine of the angle in diamond. So let's plug in whatever values we have here. So if we are trying to find the angle in diamond, we just block this. We just have to take sine W divided by the refractive index. sine of the angle in diamond is equal to sine of the angle in water divided by the refractive index. Sine D, which is what we don't know as yet, sine W is how much? Sine W is sine 60 degrees, and the refractive index from water to diamond is 1.12. All we need to do is find sine 60 on our calculator, divided by 1.12. You will get a decimal. To solve for D, you throw across the sign to get sine inverse. So after you divide these two, the decimal you get sine inverse that decimal, and that will give you the value of the angle in diamond. So sine 60 divide, let me do this one on our calculator. Brilliant. Not too sure if y'all can see this. Raise the brightness here. Now I don't think you all can see the calculator, but I'm going to put it here just in case. Alright? Maybe when I edit it, I'll get it to show. Sine 60 divided by 1.12, and then I sine inverse that answer. Second function sine, and I get roughly 51.9 degrees. So you can call it roughly 52 degrees, the approximate value, depending on how you round off. So the angle in diamond is 52 degrees. Now, I just want to recap on this question. This was a refraction question, and we were not given the refractive index. So I had to use formula 6 to get the refractive index. And once I got the refractive index, I used that answer in formula 5. Alright, so it had 2 steps. You can expect a lot of marks for a question like this in the exam, right? Because there's so many steps. Also, I have to, if you have trouble making out the small handwriting, try viewing this video on a laptop. Okay? Alright, let's try another question. Right. This is actually a strange multiple choice question I came across a couple days ago. So let's try it. A lot of students would get trouble with a question like this. You have 2 waves on identical strings, and they have frequencies in a ratio of 2 to 1. If their wave speeds are the same, how would their wavelengths compare? Usually, well, this let's go to the first formula. Velocity is, let me draw this here. Velocity is frequency multiplied by wavelength. Let's just let's just make velocity the subject of the formula. So if we want to find velocity, velocity is just frequency multiplied by wavelength. So apparently we have 2 waves. Let's draw any 2 waves here. Wave 1 and wave 2. Simple as that. Right. So let's just say the first wave has a frequency twice the second wave, because a ratio of 2 to 1 means that this frequency is twice this frequency. So let's call his frequency 2f and the frequency of the other wave just f. You notice 2f is twice as big as f. They also said, right, that their speeds are the same. So that means if he has a velocity v, the second wave also has a velocity of v. So they're asking, how would their wavelengths compare? Alright, so let's see. Let's form an expression for this one here. How would you calculate the velocity of this wave? Well, the velocity is what? Frequency multiplied by wavelength. So the velocity of this wave is v, and to calculate his velocity, we take his frequency, which is 2f, and we multiply it by the wavelength. So I'm just going to call this wavelength 1, because we do not know anything about their wavelengths as yet. For the second one, let's calculate his velocity. His velocity is also v. So to calculate his velocity, we take the frequency, which is just f, half this value, and we multiply it by its wavelength. I'm going to call it wavelength 2 because we don't know anything about this wavelength. So we have two equations here, equation 1, equation 2. Here's what I suggest. Let's divide equation 1 by equation 2. Remember in maths, whatever you do to one side, you can do it to the other side. So let's take this side of the equation and divide them. So we get V divided by V is equal to the 2F multiplied by lambda 1, wavelength 1, divided by F multiplied by wavelength 2. Right? I think there's something underneath this paper here. Oh, there's a little rock. All right. So let's divide. V into V is 1. 1 divided by 1 is 1. The F and the F will cancel out. So what we end up here is 1 divided by 1 is equal to, we cannot divide lambda 1 by lambda 2. Well, we can't cancel them off because we don't know if the wavelengths are the same. But we end up with 2 lambda 1 divided by lambda 2. So if we cross multiply, 2 lambda 1 is equal to 1 by lambda 2. So this is the relationship between the two wavelengths. If I make lambda 1 the subject, I throw across the 2, which is a multiply, I'm going to get a divide. That means for me to get the wavelength of the first wave, I have to take the wavelength of the second wave and divide it by 2. So let's put some numbers to that. So wavelength 1 is equal to wavelength 2 divided by 2. So that means if the wavelength of the second wave was 10 meters, then the wavelength of the first wave, right? Remember the wavelength of the second wave is 10. To get the wavelength of the first wave, we just take 10 and divide it by 2. That will give us a wavelength of 5. So which one is always bigger? The second wave, his wavelength is always twice as big as the first wave. So if his wavelength was 100, he would be 50. If his wavelength was 8, his wavelength would be 4. So the wavelength ratio of wavelength 1 to wavelength 2, notice wavelength 2 is always twice as big as the first one. So it will be 2 to 1, right? Or you can write it with wavelength 2 if you want to switch it around with the bigger number first now. Sorry about the scrap here. Wavelength 2 to wavelength 1. You can just flip it around. 2 to 1. Alright. So that's 9 questions on waves. Alright. Now, in my next video, I want to discuss a little bit more about waves, but it will be more diagram based, right? There will be a lot of diagrams and how you interpret the diagrams to get values to go into your formulas. All right, so before I get into the questions, I just want to go through 3 diagrams with you all. So on the screen, 3 diagrams, one by one, will appear, and I want to discuss all of them. So the first diagram, you will see a wave, right? Now, you'll see 2 diagrams, one on top, 2 parts of the diagram, one on top and one underneath. On the top diagram is the side view of a wave. Now, you will notice that you will see the up and down motion of the wave, the displacement of the wave. The top of the wave, as you all know, is called the crest, and the underneath of the wave is called the trough. Now, from the side view, you can easily make out the crest or the trough. But that's a side view, like I said. Now, imagine that you were a bird and you were flying over the wave. It may not be easy to identify the crest or the trough. So, on a diagram, if you're viewing the wave from on the top, if you look at the diagram on the bottom, you will see a bird flying over the ocean. You represent the crest with the solid line. So every time the wave is completely to the top, at its highest point, you will see a solid line. And the troughs are represented with dashed or broken lines. So that means if you wanted to figure out the wavelength, you just have to measure the distance between two successive crests, or two successive troughs. Okay, so I just wanted to make sure you understand how to represent a wave from the side and also how to represent it from a top view. So let's look at the second diagram. Right, now this diagram shows water, like in the ocean, going from a deep part of the sea to the shallow part of the sea. You will notice that in the deep part, the wavelength, the distance between, well, in this diagram, the distance between two crests is quite large. However, in the shallow region, the wavelength is small. So you need to remember that whenever a wave goes from deep to shallow, the wavelength in the deep is actually be larger than the wavelength in the shallow. Also, in the deep region, the speed or velocity is large. However, when it enters the shallow region, the velocity decreases. So think of it like this. In the deep, everything is bigger with regards to wavelength and velocity. In the shallow region, everything is smaller with regards to wavelength and velocity. The only thing, and I highlighted it in kind of yellow and green, the only thing that remains exactly the same in the deep part and the shallow part is the frequency. So if the frequency in the deep part was 5 Hertz, that means the frequency in the shallow region is also 5 Hertz. That's the only thing that remains the same. All right, so to the third diagram. It's a good idea to take, when you see these diagrams, pause the video and draw back each diagram neatly in your book. Just watching it on the screen is not enough. So let's look at the third diagram. This diagram, unlike the one I just showed you, is not a side view. In fact, it's a top view, like a bird is flying over the scenario. Now, in this diagram, the boundary between the deep and the shallow region is not a straight line. You will notice that the deep is a kind of deep blue and the shallow is a kind of light blue. And the line is slanted, the boundary line is slanted. So the wave, and I use solid lines to indicate the crests, are headed from the deep to the shallow region. Now, a few things you need to know, and I already discussed some of them in the previous diagram, but let me say it again. In the deep part, even look at point number 1. The wavelength in the deep part is larger than the wavelength in the shallow part. You'll notice in the deep part, the distance between the lines, the distance between the crest are far apart, indicating a large wavelength. However, when it enters the shallow region, you will notice that the distance between the crest, the straight lines, are smaller, indicating a smaller wavelength. Point 2. The angle in the deep is larger than the angle in the shallow. Now, what angle am I talking about? Whenever you have a boundary, if I were to draw a line perpendicular to that boundary, you'll notice you'll see a red dashed line. That line is called your normal. The direction of the wave is indicated by the black arrows. You will notice that in the deep region, the angle between the direction of the wave and the normal is larger than the angle of the direction of the wave in the shallow region and the normal. So if you look at the two yellow circles, the circle more to the left, that angle is larger than the angle to the right. Okay? So when I'm talking about the angle, remember the angle is always measured between the direction of the wave and the normal. And the normal is always at 90 degrees to the boundary. And in this case, the boundary is the boundary between the deep region and the shallow region. Right. Now, point 3, you all already know, but I'm going to say it back. The velocity in the deep region is larger than the velocity in the shallow region. So that means in the deep, the waves move faster. In the shallow region, the waves move slower. Right, and as already mentioned in point 4, in both regions, whether it's deep or shallow, the only thing that remains the same is the frequency. Velocity will change, wavelength will change, even the angles will change. But the only thing that you can count on that will remain the same is the frequency in both regions. Alright guys, so draw these diagrams properly. Whatever notes I gave you on the diagrams, also write them down in your notebooks. And now let's begin the questions. Alright, so let's start our first question. Right, so let's read the question first, and I kind of drew a diagram to summarize what's going on, but I still think I'll need to talk it through. So here we have a wave, right, in the deep part of the ocean, and the wave is going to go from the deep into the reef. Now, the ocean is deeper and the reef is shallow. So what's going to happen, remember from the diagrams I just showed you, what's going to happen, it's coming in at an angle, and the examiner told you the angle. So in the deep part, let me get something to point with instead of using my hands. So notice the general wave direction is shown by the orange arrow. So this here is the boundary between the ocean and the reef. So, and this here is the normal. Remember, the normal, the dashed red line, is always at right angles to the boundary. So the wave in the deep part is making an angle of 75 degrees. So when the wave is coming and it hits the boundary, its angle will change. So here's 75 degrees, and here we do not know the angle. But here's what we do know. The wavelength in the deep region is 8 meters, and the wavelength in the shallow region was 2.5 meters, which makes sense. Remember in the slide I just showed you, the wavelength in the deep region is supposed to be bigger than the wavelength in the shallow region. So that makes sense. Also, the velocity in the deep region is supposed to be larger than the velocity in the shallow region. So if the velocity in the deep region is 12, in the reef, which is the shallow region, the velocity is supposed to be smaller than 12. But we'll do our calculations to see if that's really true or not. Alright, so let's start. Oh, and by the way, the only thing that's the same in the deep and the shallow is the frequency. So let's start off with A here. Right, and of course keep your eyes on the formulas at the top of the screen. A, what is the frequency in the deeper water? So there's a deep section here. So I have a feeling I'm going to end up using the first formula. No, the first formula, yes. Velocity is frequency multiplied by wavelength. To calculate the frequency in this region, we just have to take the velocity, which is 12, and divide it by the wavelength in the deep region. So frequency in the deep region is velocity divided by wavelength. My velocity is 12, my wavelength is 8. And I have the correct units. The velocity is in meters per second, my wavelength is in meters. So there's no tricks there. So let me try to work that out. 12 divided by 8 is 1.5. So when we divide these two, we get 1.5. So that means the frequency in the deep part is 12 Hertz. I'll just write the answer on the paper here one time. So, why did I write that? It's 1, I made a mistake here guys. 12 divided by 8 is 1.5 Hertz. Right? So 12 divided by 8 is 1.5 Hertz. That's the frequency in the deeper part. Now, without me reading the rest of the questions here, I just want to point out one thing. If the frequency in this region is 1.5, I'll put the Hertz here. That means the frequency in this region is also 1.5 Hertz, because frequency in the deep part and frequency in the shallow part are the same. So I'll just make a note of that one time. All right. What is the period in the deeper part? Now, when they say the period, they're already referring to the periodic time. So let's look for a formula with the periodic time. That's the one with the capital T. That's formula 3. So everyone look at formula 3. 1 is equal to frequency multiplied by the periodic time. Capital T is what we are trying to find. If we're trying to find the periodic time, it's 1 divided by the frequency. So the periodic time is 1 divided by the frequency. 1 and the frequency in the deep part, because part B is referring to the deep part, is 1.5. All right. Now, I'm just double checking a couple of things here. Right. So 1 divided by 1.5. We're going to get 2/3. Now I'm going to round it off to 1.67 seconds. The periodic time is measured in seconds. So, I'm not too sure why I'm constantly saying the wrong thing. I made a mistake, guys. Sorry about it. Just a little bit tired at the moment. Alright. Let me just do back that one. 1 divided by 1.5 is 2/3, which is 0.67 seconds. Okay. So let me write that answer in. I'm going to have a different color here. Well, the periodic time in the deeper part is 0.67 seconds, or some of you all just might write 2/3 of a second. Both of them are correct, right? One is just the rounded off version of the other. Alright, so we're done with 2 parts there. What's the next part asking us? The next part is asking us the frequency as it passes over the Great Cunupia Reef, right? Now, some of you all didn't know, but the reef that they're referring to is the Great Cunupia Reef, okay? Right. I grew up around there. My father's father grew up around there, and his father's father grew up around there. So, but I think I already answered C. C asks us for the frequency as it passes over the reef. Remember, the frequency in the deep part and the frequency in the shallow part is the same. So that means the frequency here is 1.5 Hertz also. Right? So I hope you can see that. The frequency here for C is 1.5. The period as it passes over the reef. To calculate the period in the reef part is 1 divided by the frequency. Okay? Now the thing about it, frequency is dependent on the periodic time, and the periodic time is dependent on the frequency. So we're going to get the same answer as of part B. So to calculate the periodic time, we're going to take 1 and divide it by the frequency in the shallow region. 1 divided by 1.5 will give us the same answer here, which is 0.67 seconds, or 2/3 of a second. Alright, so let's see the speed as it passes over the reef. We are going to use formula 1. Velocity is frequency multiplied by wavelength. To calculate the speed or velocity, we just have to take the frequency and multiply by the wavelength. So velocity is frequency multiplied by wavelength. In the reef part, the frequency is 1.5, but the wavelength is no longer 8. The wavelength in the shallow region or the reef is 2.5. Alright, let's multiply it. 1.5 multiplied by 2.5 is 3.75 meters per second. Alright, double checking to make sure. 1.5 multiplied by 2.5 is 3.75. So let me write that answer. The speed as it passes over the reef is 3.75 meters per second. Now, does this answer make sense? Yes. Remember, I told you that when a wave is going from deep to shallow, it's supposed to slow down. The velocity in the deep part is 12, but the velocity in the shallow region is 3.75. So that's a reduction in speed. So my answers are actually making sense. F, the angle of refraction on reaching the reef. All right, so this is an angle question, which means we need to get the refractive index. So let me get my... Alright, let's see what we have here. So, look at the top of the screen. Let's see which formula we need here first. Okay? Right. So, if we look at it, I think we will need formula 6. So, everyone look at formula 6. We need to calculate the refractive index first. And to calculate the refractive index from deep to shallow, right, using formula 6, D for deep, S for shallow, we just have to take the velocity in the deep region, which is 12, and divide it by the velocity in the shallow region. Remember, the velocity in the shallow region is 3.75. So that would at least give us the refractive index from deep to shallow, or from the ocean to the reef. So 12 divided by 3.75 gives us a value of 3.2. So we know the refractive index from deep to shallow. Using this value now, we can use formula number 5 to get the angle in the reef. So I just need to erase this space here. I have limited space on this board right now. Using rule 5, the refractive index from deep to shallow is equal to the sine of the angle in the deep divided by sine of the angle in the reef, which is the shallow region. So let's put S for shallow. Shallow and the reef is the same thing. Let's plug in what values we have. The refractive index from the deep to the shallow, remember we just got it as what? 3.2. The angle in the deep region is supposed to be 75. And we are trying to find the angle S in the shallow region. That's this guy here where the R is pointing to, right? So the angle in the shallow region, we're just calling it angle R. R could be for the angle of refraction or R for reef. What we're going to need to do is cross multiply. Remember, 3.2 is the same thing as 3.2 on 1. You will need to find sine 75 on your calculator, round it off to 2 decimal places, cross, multiply, and solve for R. Alright, I will not be showing you the calculation for that. I showed you this in the physics basic videos, parts 1, 2, and 3. So I cleared up those issues on how to solve these types of equations. If you haven't watched those videos as yet, please take a look at them. Alright, so I'm just going to solve it here quickly, right, on my calculator. Sine 75 divided by 3.2. And we will get roughly, if we do this, R is going to be 17.6 degrees. So this angle here is going to be 17.6 degrees. You notice the angle got smaller. Right, so let me write that in. Oh, running out of space here. 17.6 degrees. Right. The refractive index on traveling from deep to the shallow. But we already worked this out. We needed to actually work this out to get part F. Remember, the refractive index from deep to shallow was 3.2. Alright, so I really hope that this question made some sense, right? As I said, if you need these questions, right, please feel free to WhatsApp me on 1-868-712-2652, right? I just ask for the wave questions, right? And I will send you a PDF document so you can actually print out the document, and while I'm doing these videos, you can fill in your answers or do your working on the PDF document itself, provided that you printed it out. All right, let's try another question based on these kind of top view diagrams. All right, so let's try a second question. Now, this question involves a wave going from air trying to go into a balloon, and inside the balloon it's filled with a gas called argon, right? So in this question, when the wave, and you will see the wavelength here, the wavelength is 20 meters. When it's going from air into the balloon, the only thing that will remain constant is the frequency. Just like how when the wave was going from deep to the shallow region, we said the frequency will remain the same. This here is a very similar situation. Instead of from deep to shallow, it's from one substance, air, into another substance. And you have to keep in mind that when it goes from one substance into a next substance, you can expect the velocity to change. So it can either get slower or it could speed up. And you can expect the wavelength to change. So right now the wavelength is 20. So inside here, it might be a bigger value or a smaller value. We do not know as yet. The only thing that will remain the same is the frequency. And you will notice in this case here, the wave is not coming in at an angle. Not to say it's coming in this way. It's coming in line with the boundary. So if it's coming in line with the boundary, you can expect the direction to remain the same. The angle will not change. The only time the angle changes is when the waves come in at an angle. In this case here, the angle it's coming in with is 0 degrees. All right, now here's a formula we haven't gotten around to use as yet. This is equation 6. Now, equation 6 is an equation that arises out of the fact that frequency remains the same. So, the velocity in A divided by the wavelength in A is equal to the velocity in B divided by the wavelength in B. In other words, this is the first substance, which is air, and after the equal sign is the second substance where the wave is headed into. So let's use this formula and figure out what happens to the waves when it goes from air to the balloon. Right, so let's just substitute in the values. The velocity in A is 330. The wavelength in A, remember the solid line represents the crest, and the distance between two crests is the wavelength. Now I know the wavelength wasn't mentioned in the question. I forgot to write it in, so I drew it on the diagram, right? So this 20 was supposed to be inside the question. What's the velocity of the wave in the balloon? They told us that when it entered the balloon, it traveled at 480. And we are wondering what happens to the wavelength inside the balloon. So all we have to do is cross multiply. 330 multiplied by wavelength B is equal to, give me a few seconds here, 480 multiplied by 20, which is 9,600. To solve for this, we throw across the 330, which is a multiply, it becomes a divide, and we get roughly, I'm just going to put the nearest whole number, 29 meters. So, in a case like this, the wavelength went from 20 and inside the balloon is 29. So if I had to draw the wavelength inside the balloon, I would have to make sure that the spaces between the crest looks a little bit bigger from here to here, because 29 is bigger than 20. So if we can draw something like this, like if it was inside the balloon, we just make it a little bit bigger. So that means the distance between here and here is 29 meters. And it makes sense. Let me explain why. Remember, the velocity inside here is 480. If the velocity were to get larger, you can expect the wavelength to also be larger, right? Now remember, this was a rounded off value. It was 29.09. So if you wanted to be super accurate, 29.09. And we can actually test to see if this answer is correct, you know. And if we use Formula 1, velocity is frequency multiplied by wavelength. How do you calculate frequency? Frequency is velocity divided by wavelength. So let's write that down. Let's calculate the frequency in the air and then calculate the frequency in the balloon. What's the frequency in the air? Well, in air, the velocity is 330 divided by the wavelength, which is 20. And you will see that the frequency outside here is 16.5 Hertz. Let's calculate the frequency inside the balloon. The frequency inside the balloon is the velocity inside the balloon divided by the wavelength inside the balloon. Let's see if we get the same answer. 480 divided by 29.09. Sorry, I made a mistake there. Just a little bit tired, guys, sorry. So it's 480 divided by 29.09, and we got roughly the same answer, 16.5. So the frequency inside here is 16.5. Remember we said when a wave changes substances or it goes from deep to shallow, the only thing you can expect to remain the same is the frequency. All right, guys, let's try another question. All right, guys, let's try another question. Here we have a top view diagram once again, and what we have here is water waves coming from the Cunupia Great Lake, and it's trying to enter the Cunupia Not So Great Lake. Now, obviously, we're going to assume that the depth of both lakes are different. I'm not saying which one is deeper and which one is, shallow as yet, okay? We'll do the calculations and determine which one is deeper and which one is not as deep. So what's going to happen here, before I do this question, I want to do it a slightly different way. If you look at the top of your screen, you will see two formulas, Formula 5 and Formula 6. Now here's what. I'm not going to go through all the details, but if you were to combine Formula 5 and Formula 6, you would get this equation. So I want you all to take down this equation and call it equation number 7. And it's a very useful formula. It can make your calculations move quicker, I guess. All right, so let's see what's going to happen here. So you'll see in your formula it has A and B and A and B. We're going to assume that everything in the Cunupia Great Lake, all its values will be A, and everything in the Cunupia Not So Great Lake will be B. So according to this, the angle A is 20, and the velocity in A is 25, and in B, the Not So Great Lake, the angle in that is 35, and we do not know the frequency. So what we have to do is two things. And we do not know the velocity. We have two things to find in this question: the velocity in this region and the frequency in this region. But I'm sure you already figured out that whatever we get for the frequency in this region will have the same exact frequency, because both, the only thing that doesn't change when a wave goes from deep to shallow or shallow to deep is its frequency. Everything can be expected to change. So let's plug in the values over here. So I just discussed the values. Let's plug it in over here. So I know you can't see the paper right now, but I wonder if I put it below here. No, you still can't see it. So I'm just going to talk you through. The velocity in A, in the Great Lake, is 25. We do not know the velocity in the other region, right? We do not know the velocity in region B. So I'm going to leave it as VB. The angle in region A is 20 degrees. And the angle in region B is 35 degrees. That's the not so great lake. So to find the velocity B, we will just need to find sine 20 on our calculator, round it off to 2 decimal places. Find sine 35, round it off to 2 decimal places, and then we can just simply cross multiply. I will not be going through this calculations. Once again, please review the 3 physics videos for beginners. It will help you through the mathematical portion of the syllabus. Alright, so I'm just going to do this quickly on my calculator. Let's see what I get. When I solve for VB, I get 25 multiplied by sine 35 divided by sine 20, and I get roughly, and I say roughly, 42 meters per second. So that means my velocity in this region here is 42 meters per second. Right. So if you go back to the beginning of this video and view the little diagrams I drew, in the deeper region it moves faster. You will notice in region B the velocity is 42, while in region A the velocity is 25. So that means the velocity here is larger. So that means for some strange reason, here is the deep and over here is the shallow. Who would have thought? Alright, so for some reason the Columbia not so great lake is the deeper one. So I'm just saying, in the deeper region the wavelengths are supposed to be further apart. So if I had to complete the diagram, I would probably draw it like this. You'll notice the distance from here to here is smaller than from here to here. In the deeper region the wavelength is supposed to be larger. So that's just if I was asked to like draw how the wave in the deep region might look, right? I don't know the exact spacing of it. All I know, it has to be bigger than this. All right, now there's another thing we have to find here, the frequency. Let's go back to formula 1, right? Formula 1. Velocity is frequency multiplied by wavelength. We want to know the frequency. We can take any region. Let's just remember the frequency in this region and the frequency over here is the same. Let's use this side. We know the velocity in this region is 25, but nowhere in the question they gave us the wavelength, right? So, but if you notice at the top of the paper here, it said it's drawn to scale, which means that I can actually use my ruler to figure out the wavelength. All I have to do is figure out the distance between the two waves, the two crests, sorry. And if we do that and we measure it, we get roughly, I'll put it here, we get roughly 3.2 centimeters. So I know the wavelength. So to find the frequency is just velocity divided by the wavelength. But the wavelength for this formula has to be in meters. So I have to take this 3.2 and divide it by 100 first to get 0.032 meters. And that's the value I can put here, 0.032. So to find the frequency in hertz, take the velocity, which is 25, and divide it by the wavelength. So we take 25 and divide it by 0.032. And we get, I'll put the answer here. Get a little glare on my calculator. We get 781.25. And this answer will be in hertz. And remember, we found the frequency on this side using the velocity and the wavelength here. But like I said, the frequency in the shallow and the deep region will be the same. Alright guys, so I really hope that this video was helpful. Of course, don't forget to subscribe, and please don't forget to share this video. If you know anyone who's having trouble in physics, please share. And of course, if you're interested in my lessons and you're from Trinidad and Tobago, you can always call me to book a space in my class on 712-2652. Obviously, this is only for people who reside in Trinidad and Tobago, right? So feel free to call me, guys, to book a space. Take care and good luck in your exams.